Welcome back to the third part of the lecture about inferential data analyses. In this part of the lecture, I'm going to take you briefly through some of the tests that you will read about as you study these research articles. Remember, I want you to have a conceptual understanding. For example, in a quiz, I may ask you to match up a test with a particular situation. You don't need to know how to do the test. I want you to understand whether or not that test would probably be appropriate for that. So just a quick review. When I'm talking about inferential statistical analysis, I'm talking about tests that we run that measure whether that difference between the groups is by chance or not. And I'm gathering evidence to reject the null. You'll remember what I talked about in the last lecture, I hope. What we come up with is this concept that's called statistical significance. And that's saying mathematically, statistically, there is a difference between the groups, and it's statistically significant. There can be a difference between the groups, but if it's not statistically significant, that means it's not large enough to measure, and there's a probability that that difference is just there by chance. So I have to set my statistical significance. We also can do this when we're talking about relationships. So we're saying that the relationship in the variables is strong enough to measure, and that the probability that it's just by chance is very, very small. Then I have statistical significance. There's a lot of things that affect the significance. So you need to be kind of careful about this. There's a lot of ways to show statistical significance, and you can even change the test you're doing and show statistical significance. So you have to get you have to be very, very cautious about this. There may be actual differences between the groups to start with. There could be sampling and measurement errors, and remember that I talked about the size of the sample. If my sample is large enough, ridiculously large, it's going to be very, very easy to show statistical significance, and yet that may not mean a thing. So when you look at what an author says they've reached statistical significance, look at the descriptive statistics that are given and kind of try and make a determination that, does this make sense? Go back to the kurtosis and the skewness and look at that standard deviation and different things like that. It's also really, really good if an author will give you a confidence interval. And I'll explain that more in a minute. But basically what it means is they're giving you a range and telling you how confident they are that the real, in quotes, value is somewhere in that range. Another thing that we really encourage in all data analyses is, were they able to come up with an effect size? Which is that how strong is that relationship, or how big is that difference? I can show that something is statistically significant, but if the effect size is so small, oh well, it doesn't help anything in the world if the effect is so small, even though it may be significant. Let me give you some examples of confidence intervals. When we're using confidence intervals, it's really important because what the researcher is doing is saying, I'm acknowledging and I'm being really upfront that the statistic I came up with is an estimate, that it's an estimate based on the sample. And we use the variability in the scores, that distribution, to show a range that likely holds the true value. So if I have some kind of measure and the mean is 54, what you will see a researcher say is that they have a 95% confidence interval of 52 through 56. And what that means, if you look on the number line, I've shaded in between 52 and 56. What that means is that the author, the researcher, is 95% certain that the actual population mean is somewhere between 52 and 56. A lot of confidence, but at least acknowledging that it's an estimate. and not saying that the mean is 54, and that will hold true for the population. A lot better to use a confidence interval, and not nearly enough researchers actually do this. Now, when you're looking at effect sizes, here are some things to look for when the researcher says they found an effect size. There's different measures. There's R-squared, which deals with relationships and the effects that each variable has on another. You will see words like partial eta squared or eta squared, Cohen's d, Cohen's f. This is a good slide to flag, because when you come across these terms, the bottom line is the researcher is saying, I measured an effect size, how strong the relationship was or how large the difference was between the groups. So I'm going to give you an example here with Cohen's d, which is a very, very common one. You've got two groups. Cohen's d can only be used with two groups. And what it does is it's a test that measures how different the two means are. In other words, how much overlap is there in their distribution. And look down there at the bottom. You see the mean for both of those distributions, and there's some overlap between them. And that's what Cohen's d is measuring. If there's a large overlap, in other words, those two distributions are almost on top of each other, there's a very small effect there. There's not much difference between those two groups, and there's a small effect. And that's what Cohen's d is measuring. So when you see Cohen's d, this is another good one to flag. A very small effect would be a 0.2. Sometimes in education research, that's about as good as it gets. A medium would be a 0.5, and a large effect would be a 0.75. Very, very seldom seen in research. Very hard to come up with effect sizes like that. Now, your textbook has this complicated diagram for the logic of which test to use where. And that would be a great reference. But I'm going to go through some real quick ones, some of the more common ones here, because I want you to understand them conceptually. First of all, as you do read research, you will find that the researchers are either doing parametric or non-parametric analyses. Parametric are the most common, and they use the rules and assumptions for all the normally distributed data. So they're using a bell curve, if you want to call it that, this normal distribution, and they're looking at the probability of this distribution that they find. And they use interval measurements. Non-parametric inferential tests are much more difficult to do, and they're much less common, and they are not done as well in most research because they take an incredible skill level. First of all, the non-parametric analyses are done when there is no distribution, when the distribution just is not anywhere near normal. So you have to do completely different tests if you're using non-parametric data. You will see tests that are done for univariate tests. That's a word you will run into a lot. You need to understand what it means. That means there's a single dependent variable and a single independent variable, the simplest way that you can do it. And then you will find multivariate inferential tests, and that means that the researcher can be using multiple dependent variables and or multiple independent variables. And you can imagine that the more you get, the more complex it goes from there. Now, what we're doing when we run an inferential test is we are looking for a critical value in the test that we run. And what that is it's the benchmark or the criterion for statistically rejecting the null. And if you look in your textbook on page 301, you'll see a table of numbers there. Down the left is the degrees of freedom, and that's related to the sample size. So if the degrees of freedom is very, very high, there were lots of people in the sample. If it's low, there were just a few people in the sample. And basically, when you run the test, your result has to meet or exceed, not of exceed, that number in the table to be statistically significant. So if you look at the table, if you'll turn to page 301, this is a t-test. A t-test means there were two groups. And when all the tests were run, the statistic was 2.3. At a 0.05 significance level, remember I talked about that before, you're going to reject the null because t at 9 degrees of freedom, 2.3 is above that critical value number. However, same degrees of freedom, 9, if you ran the test and your test statistic ended up being 1.7 at the same significance level, that's below that critical value in the table. So you do not reject the null hypothesis. T-tests. First kind of analyses that I expect you to conceptually understand. When someone is doing a t-test, they are comparing two groups, two means. Any more than that, it's not a t-test. There are two kinds. There's the independent samples t-test, and that means you've got two groups, two samples, same test or measure. So it would be something like, do males and females differ on spatial tests? Two groups, males and a group of females. And are they different on this test that we give them? I would run my t-test and I'd see if that number was above or below the critical value. Dependent or paired samples, though, are different. That means the groups are related somehow, or we're using the same group twice. So if it's a dependent or paired samples, it means that maybe there's a pre and post test. That's the most common way that you'll see this done. And so you've got a pre-test, and then you say, do individuals who eat oatmeal for 6 weeks decrease their cholesterol level? So obviously we tested their cholesterol level, they ate the oatmeal, and then we tested it again. So that's a dependent t-test. The group was tested twice. You calculate a t-test statistic and look at whether it meets that cutoff for the critical value. And that's all there is to it. See how easy it is? ANOVA is another very, very common, especially in educational research. It stands for analysis of variance, difference, in other words. And you use two or more groups. Remember, a t-test was only good for two groups, just a simple comparison. But you have to run an analysis of the variance, of the differences among the groups, if you're going to have more than two groups or means. So, and in this example, we've got three groups. We've got a Protestant group, a Catholic group, and a non-religious students group. And so we could say, is there a difference? Do Protestant, Catholic, and non-religious students' attitudes towards same-sex practices differ? And then we would run the test to see if there was a difference in the attitudes of those different groups. This would actually be a one-way ANOVA. It's got one independent variable, which is the religious affiliation, and it's got multiple levels or groups. There's Protestant, Catholic, and non-religious, and there's one DV, so it's a one-way ANOVA. And we're same as with a t-test, same idea as a t-test, only this time with an ANOVA, it's called an F-test statistic. And again, there's going to be tables for F-test statistics, and you look and see if your number is above or below that critical value at your level of significance. Really, really simple. Now, I talked to you in an earlier lecture about factorial ANOVA. Remember when I talked about interactions? You may want to pull that out again. When you've got multiple IVs, independent variables, you're going to have to calculate many, not you, the researcher is calculating test statistics for the main effects and then calculating the test statistic for the interactions. So it's not always straightforward one F test statistic and it's good or bad or whatever, or it's significant or not. You have to calculate the different statistics for each type of effect with the factorial ANOVA. And this is where it gets really fun. So there could be a main effect. Does student car ownership influence the participation in after-school activities? So the dependent variable there is the participation. The independent variable is whether or not the student owns a car. There could be another effect, main effect. We've got two IVs going here. Does GPA influence participation in after-school effects? So I've got two different independent variables. I've got one that says, does student car ownership, and the other one is their GPA. And I want to see how those two together influence the participation in after-school activities. So I have to calculate a lot of test statistics. Calculate one for the car ownership influence. I calculate one for the GPA influence. And then I calculate a test statistic for the interaction when I look at both of them together. Does participation depend on car ownership and GPA? And that's what we call the interaction effect. You will see research about ANCOVA, which is the analysis of covariance. And what this means is that the researcher has identified a variable or a characteristic that he or she knows is influencing the outcome, and actually removing that or adjusting for it. So a covariate is introduced. And it's not appropriate if there are huge differences in the groups pre-test, but it's very, very common. So if, for example, if I'm trying to look at the writing scores for two different groups, maybe I did some kind of intervention. We'll go back to that annotating informational text example. And I now want to see if there's a difference between these two groups. Well, I know from research that a student's reading level affects how well they write. There's a real strong relationship there between a student's reading level and their writing skills and ability. So I identify reading level as a covariate. I acknowledge that it's going to influence this. And so I statistically take out the effects of reading level. And then I can get at the meat of what I'm really trying to determine. And I can compare without the effects that could be attributed to the reading level of the students. So that's analysis of covariance. There are also multivariate different types of research projects. And these, as I said before, could be multiple independent variables and or multiple dependent variables. The more common is multiple independent variables and just one dependent variable. You have to get really, really good if you're going to start working with more than one dependent variable. You will see multivariate ANOVAs where there are many, many different independent variables, and these are called MANOVAs. If you see MANCOVA, they're talking about multivariate ANCOVAs. And you'll also see what's called Hotelling's T. And basically all of these mean that the researcher is looking at multiple independent variables or sometimes multiple dependent variables. And you're going to have to very carefully go through the charts that are provided and read very carefully what the research set up and what was done so that you're clear in your mind which independent variables were even being tested or were being taken, the effects of them were being statistically taken out with like a MANCOVA. Here's an example of a multivariate kind of question. Are there differences in the attitudes and performances, two dependent variables there, attitudes and performances, of students being taught with lecture, there's one independent variable, or web-based instruction? And you could see that there could be multiple levels in each of those variables. One of the really exciting, at least for me, I love doing regression analysis, is inferential statistics is when I can take a sample and make predictions that are based on a trend. And this goes back to your very basic algebra classes. You're using the equation of a line to predict what's going to happen down the road. And you're looking at the slope, the steepness of that line, and trying to determine if it's statistically different from zero. So if the line is very, very flat, that's not any different than zero statistically. So an example of that, I think I've given this example before, we can predict the price of beef next fall from the amount of rainfall in the western United States. So we take something that we can gather and we use that to make a prediction or come up with a trend. Multiple regression is a very, very powerful way of actually measuring interactions. So you can imagine that you could get the slopes and the interaction effects from many different variables on something, and then you're really doing some really cool things. You will see an inferential analysis that's called chi-square. And the bottom line is a chi-square is measuring differences in frequencies in different groups. Not necessarily a score, but a frequency. How many times is this answer given? Or how many times does this happen? And this is a very common non-parametric, probably one of the most common that you'll see. And what it does is it compares the frequencies you actually see to what you expected by chance. And is there a difference between what was seen and what you would just expect by chance? So for example, a non-parametric kind of question, do mothers and fathers differ in their number of hugs for newborns? You're not going to see a normal distribution there, are you? It's going to be frequencies of those, and then you're trying to compare whether the frequency difference between mothers and fathers is what you would just expect by chance, or is there an actual difference there? So those are some of the more common ones. Now, never hesitate when you're reading a research article to simply Google it. Google the test that was run, see if you can make sense of it, if it fits. When you're evaluating these research articles, always look about the basic descriptive statistics, because that's going to form the foundation for the inferential results. Inferential analyses do not indicate anything to do with internal or external validity. Haven't talked about that at all in this lecture. You have to look at the basic descriptive statistics to determine whether there's validity there or not. Look then for the statistical significance of the analysis. When they get that F statistic, is it statistically significant or not? Keep in mind that statistical significance, by the numbers, does not equal practical significance or something great and wonderful the world should know about. For that, you need to look at the effect sizes. And if the researcher doesn't go that far, that's not good. Any researcher worth his or her salt should go on and determine an effect size. Sample size has a huge influence in inferential statistical analysis. I just can't say that enough. If there are huge sample sizes being used, well, yeah, you can expect that by chance you're going to get those results. This is where the Googling comes in this next one. Is it the appropriate statistical procedure for that particular design? If I've got more than two groups and all of a sudden I see a t-statistic in there, t-test, that's obviously false. But should the person have done an ANCOVA and taken out the effects of a covariate instead of leaving it in there, instead of an ANOVA, and those kinds of nuances? If you can get to the point where you can pick that out, good for you. And then be really careful that the level of significance is actually interpreted correctly. You will see ridiculous things like 95% with 95% confidence, when they've got a p of less than 0.05. That is not what that means. It does not mean that I'm 95% confident. What it means is there's a less than 5% chance that all of this came up by chance. And that's a totally different thing conceptually.